Dear students, today we will discuss about electromagnetic induction. Okay? So, electromagnetic induction is a phenomenon where we are getting the magnetic field from the electric fields, and in the similar way from the magnetic fields now we are getting the electric fields. Okay? At first, before going to discuss about this electromagnetic induction, at first we have to see the magnetic fields first. Okay? The basics of magnetic fields. Okay? So, here at first if you take the properties of magnetic lines, where first magnetic lines of forces. Magnetic lines of forces are nothing but those are the imaginary curves, which are in the magnetic field. Okay? So, these magnetic lines of forces actually they gives you the path here which is followed by the north pole we can take. Okay? So, magnetic lines of forces are nothing but an imaginary line or the imaginary curves which gives you the direction of magnetic field at a point. For example, if you are taking for the case of a bar magnet, if you are taking, let us assume this is a bar magnet having a north pole and south pole we have. What do you mean by these magnetic lines of forces? That is nothing but the path followed by a unit north pole if you are taking. Okay, whatever the path it follows, means we can find these magnetic lines of forces by using a magnetic compass also. Okay. When you place a magnetic compass at any position here, let us suppose if you keep a magnetic compass here, as here we are having a north pole is present, then the magnetic needle shows the direction, due to repulsion it shows upwards, means the magnetic line of force direction at this position is towards upwards. Then if you keep the magnetic compass again at here, then it shows the direction like this, and again if you continue the path here like this, it shows the magnetic compass like this, and finally it ends on the south pole here, which means that the magnetic lines of forces are nothing but the imaginary curves which are starting from the north pole and its end on the south pole here. Okay? That is nothing but the path followed by the north pole when placed in a magnetic field, that is. Okay? Usually in case of this bar magnet, if you take, these magnetic lines of forces are like curves which are starting from the north pole and ends on the south pole here. Like this, they are starting from the north pole and ending on the south pole. And in the similar way, around that complete magnet, we are having these magnetic lines of forces are spread throughout the magnet, around the magnet here. For example, in this case, here if you take like this, the lines are starting from the north pole and they are ending on the south pole here, like this. Actually, magnetic lines of forces are closed curves, that is, as they are starting from the north pole, ends on the south pole, which is outside the magnet, that is. But inside the magnet, these magnetic lines of forces are from south pole and they end on the north pole here, like this. Okay? Outside the magnetic lines of forces are from north pole to the south pole, whereas inside the bar magnet, here the magnetic lines are from south pole to the north pole, which means that the magnetic line of force started from the north pole and finally again it is ending on the north pole only here. That is why we can say the magnetic lines of forces are closed curves. Okay? Then here the magnetic lines of forces, if you observe, here we are having more number of lines are present at the poles. So, that is why the poles of the magnet are nothing but here where we are having more number of magnetic lines of forces are concentrated, that particular point only we call that as magnetic pole. That is why if you see the definition of the pole of a magnet or the magnetic pole is nothing but the region or the point where the magnetic field strength is maximum. Okay? The position, the point or the region where the magnetic field strength is maximum, that you call that as magnetic pole. As we are having the strength is more at that point, so that is why here the number of magnetic lines are concentrated at that particular point. Those only we call that as poles of the magnet. Actually, if you see the magnetic lines of forces of properties here, if you observe, all these magnetic lines of forces, they are never intersect at a point. Okay. See, if you observe here, any of the magnetic lines of forces, if you see, all those are maintained some distance between them, which means that no magnetic line is intersecting the another one. We can say these magnetic lines of forces are like going parallel to each other. Okay. And not only that, you already know that as these are closed curves, okay, which is starting from north pole and ending back onto the north pole here, and here I said all are going parallel to each other here. And not only that, the position or the point where we are having more number of lines are present, at that particular point we are having more magnetic field strength is present, which means that the number of magnetic lines of forces is directly proportional to the magnetic field strength at that particular point. Okay. And not only that, here if you see the position where at any point you take on the magnetic line of force, for example, if you are taking a point at this point on the curve of the magnetic line here, the tangent you drawn at that particular point gives you the direction of magnetic field in that region, which means that the magnetic lines of forces gives you the direction of the magnetic field at that point. Okay. So, not only the magnetic lines of forces are directly proportional to the magnetic field strength, it also gives you the direction of magnetic field at a point. So, that is why if any two lines intersect at a point, then we may have infinite number of directions we can draw at that point. That is why they never actually intersect at a point. The main reason why they are not intersect at a point is each magnetic line here, it is behaving like a magnetic pole. For example, in this case, if you are considering this magnetic line here, which is started from the north pole, it behaves like a single separate magnet, like a single north pole, and this line is also, as it is coming from the north pole, this also acts like a single north pole. That is, as two north poles are present, we already know that like poles of a magnet repel each other. So, that is why between these two lines we are having a repulsion is present. Not only these two, any of the different magnetic lines of forces you take, always there is a force of repulsion is acting between them. Actually, they have to go parallel to each other. Why it is bending like a curve and it is going from north to south pole is, here inside the magnet we are having the magnetic lines of forces are going in opposite direction, which is from south pole to the north pole. Means there is a force of attraction is present between this magnetic line and this magnetic line. So, that is why instead of going straight here, those magnetic lines are bending towards the south pole there, because of due to the attraction, because this is acting like a south pole, this is acting like a north pole here. So, that is why unlike poles attract each other, that is why they are bending like curves here. These are the magnetic lines of forces properties we have. Okay, of which the first one is magnetic line of force is nothing but it is the path followed by the north pole, that is nothing but path followed by the north pole. And next one, the position where we are having more number of magnetic lines are present, that particular position we call that as a magnetic pole, that is called as magnetic pole. The concentration of magnetic lines are more, at that particular point we always have more magnetic field strength is present, which means that if you are taking the magnetic lines here, these number of magnetic lines is directly proportional to the magnetic strength at that point, that is directly proportional to the magnetic strength. Okay. And not only that, these magnetic lines of forces, all those are of closed curves we are getting, those are of closed curves, that is. Okay. And here the direction at any point you take, the tangent is giving you the direction of the magnetic field at a point here on the curve of the magnetic lines of force. Okay. So, and the next one is we already seen that magnetic lines of force are starting from north pole to ending on the south pole, and it is going from south pole to the north pole, that is. Okay. These are the properties of magnetic lines of forces, particularly in case of a bar magnet we are taking. Now, we will see in case of bar magnet, as the magnetic lines of forces are like this, then in case of during the attraction and repulsion between the poles, how the magnetic lines are present is here, when you are bringing two unlike poles closer, means bringing a north pole and a south pole near one to each other here, then how the magnetic lines of forces are present is, for example, if this is one bar magnet having a north pole and this is another bar magnet of which we are having a south pole is present. Then if it is going from north pole and south pole, we already know that the magnetic lines of forces are starting from the north pole and ends on the south pole here. So, that is why as this is a single separate magnet having a north pole and south pole, this is another magnet having a north pole and south pole, and these two magnets are bringing closer to each other. Then usually as the magnetic lines of forces are starting from the north pole here, then the magnetic line which is starting on one of the magnet, actually it ends on the south pole of the other magnet here, for example like this, which means that we are having a contact, the relation between the north and south here. That is why it is called as attraction, that is called as attraction. So, when you are bringing a north pole near to a south pole here of another magnet, here we are having a force of attraction is present between them like this. Here we are getting the magnetic lines like this. Like this. Okay. This is the case if you are having a north pole and south pole is bringing closer to each other. But if you are bringing two like poles closer to each other, bringing a north pole towards another north pole here of a magnet, then how the magnetic lines of forces we are getting is bringing a north pole towards the south pole here over. Now, we are seeing to the north pole, another north pole we are bringing. Here the magnetic lines are starting from the north pole, that side also magnetic lines of force are starting from the north pole. Then each magnetic line of force is behaving like a separate north pole here. So, that is why north pole repel each other, that is why they are moving away from each other here. Like this we are getting the magnetic lines of forces here. Like this. This is the case if you are having a two like poles if you are taking. You can take for the case of north pole or even you can take in case of a south pole also. In both the cases we are getting here there is a repulsion is coming and no two magnetic lines are in contact here. All are going away from each other. This is the case of magnetic lines of forces present when there is a attraction is present and when there is a repulsion takes place. Now, we will see what is this electromagnetic induction is. As we seen already about the properties of the magnetic lines of forces. Actually, for the first time this electromagnetic induction had been observed by 𝗬𝗏. His name 𝗬𝗏. 𝗬𝗏 discovered that whenever if you are taking a current carrying wire, you can take any of the current carrying wire. When you are taking a current carrying wire here, what he observed is if you bring a magnetic compass near to that, actually it shows deflections towards this current, which means that when there is a current is present, then immediately here we are getting a magnetic field is present around that current carrying wire. But remember here current means there is a flow of charges present. Whenever a charge is at rest, if you are taking a charge Q which is at rest, around that we are having only magnetic field only, only electric field only present there. If you are taking the charge there which is at rest, charge at rest. If you are taking the charge at rest, only around that we are having electric field only present there. Around that we are having electric field is present. But once the charge starts moving, if it is gaining the acceleration here, once the charge starts moving, then what happens there is around that not only the electric field, here we are also getting magnetic field also, means around that we are having the electric field as well as the magnetic field also present here. This is what discovered by 𝗬𝗏. In his activity what he done is, whenever he is using a current carrying wire here like this, a current carrying wire of which connected to a battery there like this. Now, what happened there is, what he observed is, whenever he put a magnetic compass near to this current carrying wire, what he observed is there is a deflection comes in the direction of the current here. Actually, this magnetic needle shows the deflection only if there is a magnetic lines of forces are present, or if there is a magnetic field is present. But here, without taking any magnet, only the current carrying wire if you are taking, what he observed is it is showing the deflection. Once you change the direction of the magnetic compass to the other side, then again it shows the deflection towards this current like this. Okay. So, that is why from this we can conclude that when there is a current carrying wire is present, around that we are having a magnetic field is present there. Or not only, we can also say that whenever if a charge is moving, because current is nothing but the rate of flow of charge. So, that is why here whenever there is a charge is moving, whenever the charge is getting accelerated, around that we are having a magnetic field is present. Okay. Now, if you are considering about this a straight conducting wire, if you are taking a straight conducting wire of which the current is passing through that, which is, let it be, that is I. Now, the magnetic lines, how they are coming around this current carrying wire is by following a very important rule called right hand thumb rule, or it is also called right hand grip rule also, right hand thumb rule. Okay. According to this right hand thumb rule, when you are taking a current carrying wire, okay, if you hold the current carrying wire in your hands, if you assume if you are taking the right thumb which is taken in the grip in the direction of the current carrying wire, say for example here the current is going upwards, then we are holding the current carrying wire pointing the thumb towards the direction of the current here which is upwards. Then to hold that current carrying wire, in which direction you are curling your fingers like this, and the thumb pointing upwards, and here we are curling the fingers like this. Then the direction of the curling fingers gives you the direction of the magnetic lines of forces around the current carrying wire. Okay, see that again. So, right hand thumb rule is, if you assume if you are taking this current carrying wire into your hands, then if you are pointing the thumb in the direction of the current going, and whenever if you are holding that conductor, in which direction we are curling the fingers, in which direction we are curling the fingers to hold that curling fingers gives you the direction of magnetic lines of forces. So, magnetic lines of forces are like this around that current carrying wire. In the same way, if you are taking the current carrying wire, if you are taking the direction of current reverse which is going downwards now, then if it is going up, we are curling the fingers like this, but if you are going downwards, then we are taking the direction of current which is towards downwards, and we are taking the thumb here downwards, and we are curling the fingers in the opposite direction like this. Means here now the magnetic lines of forces are going like this. Okay. So, in the first case the magnetic lines of forces are going in this direction. Now, here in the other side, now we will see the magnetic lines of forces are curling in the opposite direction here like this. Okay. This is called right hand thumb rule, which gives you the direction of magnetic lines of forces around a current carrying wire. The same way, if you are taking, for suppose if the current carrying wire, if it is coming out of the plane, means let us assume if this is the board which is our plane, so that from the plane the current carrying wire is like this which is coming outside here. Then we have to hold, according to the rule, we have to hold the thumb here in the direction of current which is pointing towards you, and we are curling the fingers like this, we are curling. So, the direction of magnetic lines of forces, whenever if you are taking outside the plane here, then the curling fingers are in this direction out of the plane, that is a anti-clockwise direction, that is. So, means whenever if you are taking out of the plane, the magnetic lines of forces here, if the current is coming out of the plane, then the magnetic lines of forces are coming around that one like this, which are in anti-clockwise direction. But if you are taking into the plane like this, if you are taking, means the direction of current is like this, into the plane, then it becomes into the plane In this case, we will get the direction of the current as it is into the plane, it is curling fingers like this, which is like a clockwise direction, always into the plane clockwise direction and out of the plane anti-clockwise direction. So, like this we can find the magnetic lines of forces direction around the current carrying wire, that is, this is called right hand thumb rule or right hand grip rule, that is. Okay. Now, if you are taking the magnetic lines of forces around this current carrying wire, which is a straight current carrying wire here, if you see the properties here, these magnetic lines of forces are always directly proportional to the current if you are taking inside that. Means whenever if you are increasing the strength of the current, gradually the number of magnetic lines of forces also increases here. Okay. Means here the number of magnetic lines, is directly proportional to the strength of the current, that is directly proportional to the strength of the current. And not only that, here these magnetic lines of forces are like closed curves around the straight conducting that wire, that is. So, means those are of closed curves around the current carrying wire, closed curves around the current carrying wire. Okay. So, the number of magnetic lines are directly proportional to the strength of the current and those are like closed curves around the current carrying wire, that is. Actually, they are coming like a concentric circles around this current carrying wire. For example, if you are taking it is out of the plane, of which here we are getting the magnetic lines of forces are around that, like this it is. Then we are curling the fingers in this direction like this. Then how they are coming is around that magnet here we are having around that current carrying wire, those are coming like concentric circles. Concentric circles means here we are having a same center is present for all the circles here, concentric circles, they are coming like this, all concentric circles. This number of magnetic lines of forces depends on the strength of the current we are passing here. It depends on the strength of the current here. Okay, if it is taken upward direction like this. Okay. Now, if you reverse the direction of current here, these magnetic lines of forces also change their direction here. Means if you are taking the same current carrying wire which is going taken downwards here, if you reverse the direction of the current, then the direction of magnetic lines as it is going into the plane now the curling fingers comes in opposite direction, which is like clockwise we are getting like this, in a clockwise direction. Okay. Like this we will get the current carrying wire, the direction of magnetic lines of forces here, if downward direction and it is taken in the upward direction, that is. Okay. So, if you are increasing more and more the current here, gradually the number of magnetic lines which are coming around that also increases here. These are the properties of magnetic lines of forces which are present around a straight conducting wire. Now, we are seeing the magnetic lines of forces, this time around a circular coil we are taking, okay, around a circular coil. Now, circular coil is nothing but here we are taking a straight conducting wire only, but that is bent like a circle here like this. Like this, a current carrying wire, now it is connected here, okay, like a circle. Okay. Now, as the current is passing through that here, going up here and coming down here like this in this circuit. Now, we are taking the magnetic lines of forces around this circular coil, and now the plane we are taking here is at this point like this. At here, now we are taking the magnetic lines of forces in this plane. Okay. So, at these 2 points, let it be at this point A and at this point B. What we observe is, in the case of the point A, the current here passing is coming upwards, which is coming out of the plane here like this. Whereas in the same coil only at the point B, the other side here, the current is now coming downwards like into the plane here. At A, out of the plane upwards, at B, into the plane inwards, that is. And we already know that once the current it is going upwards here out of the plane, then what happens there is we have to curl the fingers in this direction like anti-clockwise direction, that is. Then at this point, now the magnetic lines of forces are coming around this one like this, okay, in anti-clockwise direction, that is. Whereas in case of at the point B, now if you observe here, the current is now into the plane like this downwards. Then we are curling the fingers in which direction, that is taken as a clockwise direction, that is, as it is into the plane. Now the magnetic lines of forces here are coming around that like a clockwise direction like this, okay, curling the fingers like this. So that is why here in case of when compared to the straight conducting wire to the circular coil here, as this is a circular coil, in case of this circular coil carrying current, okay, when compared to the straight conducting wire to the circular coil here which is carrying the current here. Now in case of straight conducting wire, throughout that conducting wire we are having the direction of current remains the same. As the direction of current is towards same here, the magnetic lines of forces around that is also same. But whereas in case of this circular coil, if you see at two different points on the same coil, at one point the current is going upwards which is like out of the plane, and on the other side the current is going downwards which is into the plane here. Because of due to that, what happens there is a different two magnetic fields are coming between these circular coils here. Actually here in this case we are getting an anti-clockwise direction, whereas the other case we are getting clockwise direction here. Then if you see the properties of magnetic lines of forces about this straight current carrying wire here, which is a circular coil, if you are taking, if you are increasing more and more this current here, then what happens there is more number of magnetic lines are coming here around that current carrying wire here. And whereas not only that, here actually if you observe, as we are having two different directions are present here at A and at B here, we are getting one is acting like a north pole and other one is acting like a south pole here for the magnet. One is acting like a north pole and other one is acting like a south pole here. And if you increase these circular coils more number of turns, then always there is a more increase is present in the magnetic lines of forces also. If the circular coil number of turns you are taking, then the number of magnetic lines of present around that also gradually increases, that is. Like this, in case of circular coil, we are having two different magnetic fields are coming, having in a different direction is present. And at the point here exactly in the middle, as one case we are having upwards is there, other case also we are having upwards is there. Like this we have, okay, the magnetic lines of forces direction. At that center point, actually here as two magnetic fields which are of going upwards here, there is a repulsion is coming in between them. Okay, so that is why here they are not attracting each other. At this point we call that as null point, where the magnetic field is 0 is present. So now we seen a straight conductor and a circular coil here. Now we are taking another one which is called solenoid, which is a strong powerful electromagnet, this is, okay, which is called solenoid. Solenoid is nothing but if you are taking a insulating material like a plastic or wood, any of that cylindrical insulated coil we are taking like this, okay, like a plastic you can take. Around that we are taking a copper wire which is wounded around that one like this. Okay. Now this copper wire is now connected to a battery like this. Then the current flows through that coil like this. Then the direction, if you observe here, in one case it is coming down here going up, again coming down going up here like this. And here this direction like this. Here we are having the number of turns are present. As the number of turns are present here more in number, that's why here the magnetic field strength also more here, because the magnetic lines of forces increases with the strength of the current as well as the due to the number of turns are present here. Okay, that's why the magnetic field around the bar magnet here in this case is, as it is going in this direction here at this particular point, as it is passing like this, the current passing through at this point, then the magnetic lines of forces are around that. By taking the grip rule here, the magnetic lines of forces are present around that like this. As all are in the same direction, the magnetic lines of forces are having the same properties around that. And here down also, as all are in the same direction, the magnetic field around this one is also having in the same direction only present at here. Okay. So, this one actually if you observe, in case of this solenoid, the magnetic lines of forces are just like the bar magnet we have, because here the number of magnetic lines, the current direction is the same, here it forms a separate field, and in this direction the direction is different, it forms another field here, of which here as the current is leaving this side, then here it appears to be like a north pole, and this side it appears to be like a south pole here. Okay. So, the magnetic lines of forces which are coming here like this, and like this if you are taking, this side if it is entering and this side it is leaving, that is. So, the one which side it is leaving, that is taken as a north pole, the other side we are considering that as a south pole. Like this, here if you want to increase the field strength here, if you pass more amount of current, more strength of the current is increased, then gradually the number of magnetic lines of forces around that also increases. Means whatever the magnetic field strength here, it is directly proportional to the current we are passing. And not only that, here if you are using the number of terms here, if you are increasing the number of turns, means n value, then if you are increasing the number of turns, again what happens, there is an increase in the magnetic field strength is present, means more number of lines are there. And not only that, if you increase the length of the solenoid here, that also increases the magnetic field here like this. So, that magnetic field strength in case of solenoid, we can increase that in three different ways, of which one by increasing the strength of the current, second one by increasing the number of turns you are taking, and third one by increasing the length of the solenoid. Means the magnetic field strength here, it is directly proportional to N, I and L like this, where N represents the number of turns, I represents about the current carrying wire current there, and L represents about the length of the solenoid, that is. Till now we have seen different magnetic lines of forces around a straight conducting wire, a circular coil and a solenoid here. Now, if you see, as the magnetic field is coming here, okay, so means whenever if you are bringing a charge into a magnetic field, as the charge is moving, we are having a magnetic field is around the present around that, and again we are taking a external magnetic field is there, because of due to these two magnetic fields, there is a force is acting between them. That force now we are finding. Okay. For example, here I am taking, here if you are having a north pole and south pole is present, which means here we are having the magnetic lines are present, means the direction of magnetic field is in this direction, going from left to the right. Now, in this region, let us suppose here I am taking a charge is passing and I am moving that one. Now, let us suppose first case I am taking, if the charge is entering, okay, perpendicular to the plane where we are having the magnetic field is present, okay, perpendicular to the plane where there is a magnetic field is present. Okay. Actually, we know that according to this electromagnetic induction from Oersted conclusion that whenever if the charge is moving around that, it is having its own magnetic field is present, and here we are having external magnetic field is there. This external magnetic field and this magnetic field, they are both are showing some force is acting on that charge here. Now, that force we are taking here. We know that whatever the force it is acting, that is directly proportional to the strength of the magnetic field we are taking, that external magnetic field. Okay? The force which is acting on this charge q is directly proportional to the magnetic field strength. And not only that, here this force is directly proportional to whatever the charge we are taking, the magnitude of the charge. More and more charge if we are taking, then the force acting there also increases. And another important factor is this F is directly proportional to the velocity with which the charge is moving. Means here the force acting mainly depends on three factors here. One is the strength of the magnetic field we are applying, and the charge, how much is the charge we are taking, and third one is with what velocity that charge is moving here. As it is directly proportional to F is directly proportional to both B, Q and V, then if you are taking the relation F is equal to K constant into B Q V, that is. Okay. This is the case where we are taking if the charge is coming perpendicular to the magnetic field, okay, perpendicular to the plane of the magnetic field here. Then if you take that constant as 1, then finally we got a formula F is equal to B Q V, that is, this is the formula. Okay. This is the force acting on any of the moving charge once it enter into the magnetic field here. Okay. But actually this is the case where we are taking if it is going perpendicular there, always the force acting is maximum. But if you generalize this formula, because every time you need not to take the magnetic field here, it is taken perpendicular to the movement of the charge here. Sometimes the charge may enter making some angle there. For example, if the charge is coming into this magnetic field, making some angle there, like this also possible. So that is why if you generalize this equation, then how we will get is as F is equal to, in this case if you generalize that equation, then we will get B Q V sin theta you will get. Okay, that is of B Q V sin theta, where theta is the angle between, theta it is the angle between B and V, that is B and V, where B is the magnetic field strength and V is the velocity here, of which in which direction that charge is coming and in which direction we are having the magnetic field is present. Then F is equal to B Q V sin theta, that is, as you are coming perpendicular here as sin theta, sin 90 here, sin 90 is 1. So that is why here F is equal to B Q V, which is the maximum field we are having. But once if you are coming, if the charge is coming parallel to the magnetic field, means for suppose if the charge is coming parallel to the magnetic field here, as the angle between them is 0, then we have to take sin 0, sin 0 is 0. So that is why in that case the force acting here becomes minimum, the force acting there is minimum. Okay. So always remember that when you are taking perpendicular to that field there, always the force acting is maximum on the charge. If you are going parallel, then the force becomes minimum, that is. If it is maximum, then force it is equal to B Q V. Whenever it is minimum, the force is becoming 0. So finally we got a formula to find the force acting on a charge. F is equal to B Q V sin theta, which is for general case, that sin theta is nothing but it is the angle between the magnetic field strength and the velocity here. Okay. Whereas if you are taking for the case of maximum, means if the charge it is going perpendicular to the plane, as theta becomes 90, of which B Q V sin 90 degrees, that is, where sin 90 is 1, the maximum value we are getting is B Q V. And whenever if you are taking for the case of minimum, means the charge it is coming here, it is of parallel we are taking, of which B Q V sin 0 degrees. Then sin 0 becomes 0. So that is why the minimum force acting, that is 0, that is. Okay. But this is the case where if you are taking a single charge which is taken into the plane of a magnetic field. But if you are taking a current carrying wire inside that magnetic field, means for suppose here if you are having a plane, if this is a plane, in this plane if you are having a magnetic field is present, now in that plane, now I am taking a current carrying wire instead of a charge. As I said here, for the general case, first we are taking that current carrying wire is taken perpendicular to the plane of the magnetic field. Perpendicular to the plane of the magnetic field means, as the current carrying wire is taken here, now the magnetic field I am taking is into the plane like this. Okay. Then what happens there is, actually into the plane actually we represent with cross. Okay. Whenever if we are taking the magnetic field into the plane, that we represent with cross mark here like this, which represents the current carrying here, it is into the plane like this. Okay. Now we are taking a current carrying wire which is perpendicular to the magnetic field here. Now what happens there is, as it is of taking here which is into the plane, we have again instead of taking that Q here, here we are having the current is present. Okay. As the current is nothing but the flow of charge, then we know already the formula is BQV sin theta, that is. Then if you are taking as F is equal to BQV sin theta, here the velocity which is nothing but the displacement by time here, whereas the displacement covered by the charge here is nothing but the length of the wire we are taking. Okay. So, that displacement covered or the distance covered is nothing but the length of the coil you are taking. So, means in place of this V, we can write that is of displacement by time, which is length by time here. Okay. L by T of sin theta, that is. Then B into, if you bring this to this side, of H Q by T into L of sin theta, that is. As here Q by T is nothing but it is the charge we are taking in the given time, that is, which is called as rate of flow of charge or movement of the charge in the given time, that is. We know that that is called as electric current. So, we can write this equation as BIL sin theta, that is. F is equal to BIL sin theta. Again, as it is perpendicular here, we can take the force acting on that is maximum, which is F is equal to B into I into L, where B is the magnetic field strength and I is the current passing through the wire and L is the nothing but the length of the wire we are taking. So, the force acting in this case, if we are taking a straight conducting wire, then the force acting is directly proportional to the magnetic field strength we are applying and how much is the strength of the current if you are passing through the wire, and not only that, the length of the wire we are taking. So, this force depends on these three factors here, B, I and L. This is in case of a straight conducting wire if you are taking. For example, if you are taking a circular coil in place of that straight conducting wire, then whenever if you are taking a current carrying wire which is a circular coil, if you are getting that, then what happens there is this magnetic field, it also depends on the coil here, the number of turns. More and more number of turns you have, then we are having the magnetic field strength also increases here. So, that is why the force acting also increases. Then the new formula becomes, then F is equal to, that is directly proportional to the number of turns, that is why F is equal to N into BIL here like this. So, finally, we got three different formulas here. For the case of if you are taking only a charge, we know that F is equal to BQV sin theta, which is the general case, and after that we are having, if it is taking a current carrying wire like this, then we will get BIL sin theta, and if you are taking with a number of turns there like a circular coil, then F is equal to N into BIL, that is. If it is maximum, then theta is becoming 90, that is why we are having the maximum force is acting here. Okay. Till now we have seen how to get the force. Next we will see how to take the direction of the magnetic field, because the magnetic field strength here B and the force acting, that is a vector quantity. So, means we have to give a particular direction for that magnetic force here, okay, which is acting on the charge or on the current carrying wire, that is. Now, we are seeing how to take the direction of the magnetic force acting when if you are taking a charge or a current carrying wire inside the magnetic field. This is called right hand rule. This is called right hand rule. According to this right hand rule, how to take the direction of force is, whenever if you are taking the force, the magnetic field here which is B, and the charge we are taking, which is q and v. Now, here we are taking this charge is moving with a velocity v, that is, and we are taking the magnetic field direction, and we are taking that here the charge is moving perpendicular to this magnetic field strength here. Means, for example, like this. Here this is the charge q which is going in this direction with the velocity v, and here we are having a north pole and a south pole is present like this. Then the magnetic lines of forces are going upwards like this from north pole to south pole, that is, means the charge is coming perpendicular to that we are taking. Then how to take the direction here is, whenever if you are using that case, then we have to take here the charge which is going perpendicular to the magnetic field direction here. So, we have to take the fingers which are of, we have to take the thumb, the forefinger and the middle finger. Okay. So, thumb, forefinger and this is the middle finger. Then when you stretch that one, these three in mutually perpendicular directions, all the three. Okay. Now, always remember this forefinger represents the direction of the current here. This forefinger represents the direction of the current, whereas this middle finger represents the direction of the magnetic field strength, that is. Okay. So, always forefinger or the pointed finger, it represents the direction of current or the direction of the charge direction, that is, in which direction that is going. And middle finger, it represents about the direction of B, which is the magnetic field strength, that is. Then force is given by the thumb here. Okay. So, thumb gives you the direction of force. Thumb gives you the direction of force here, which means that, for example, if the charge is coming inside like this, then you have to take this middle forefinger in the direction of charge like this. Okay. And we are having that force here, which is the direction of magnetic field strength is upwards here, which means going from north pole to south pole, means this middle finger you have to take in the upward direction like this. Okay. Then once you stretch here the fingers like this, which is of mutually three perpendicular, that is middle finger, and this is the thumb and this is the forefinger. Forefinger gives you the direction of the charge it is moving, and this middle finger gives you the direction of the magnetic field strength. As the magnetic field strength is upwards, now I am taking here upwards, and the charge is going towards that direction, we are taking that direction the field here like this. Then the thumb is pointing towards you, that is in this direction we have, which is out of this plane, means whenever once the charge enter here like this, as the magnetic field is acting perpendicular to that, because the angle between these two is 90, maximum force is acting. So, that is why as it is this direction, it is thumb acting that direction here, the current moving direction is charge is that direction. As the magnetic field strength is upwards, then the thumb represents you the direction of the force acting. So, which means out of the plane the force is acting here. Okay. Like this we can take for any of the case the direction of the magnetic force acting. Okay. Whenever if you are taking a charge inside a magnetic field, or even for the case of current also same, as we seen in the previous example of which we are taking a current carrying wire inside a magnetic field here. For example, like this. Here we are having a plane having the magnetic field is present into the plane, of which we are taking a current carrying wire in this plane, that is like this. Here we are having a current carrying wire is there like this. Okay. Now, how the current flows, what is the direction of the magnetic force acting, we will see. Now, as I said before, first fix the direction of the forefinger here, which is nothing but the direction of charge here. Here the direction of charge means that rate of flow of charge, which is the current direction, that is. As the current direction is towards upwards, we have to take this forefinger upwards here like this. Then as I said, this is of cross represents that is into the plane, that is, which means we have to take that into the plane, and the current going is upwards. So, that is why as this magnetic field strength, this thumb represents the force, that is why here in this case the force is acting to my left side here, means in this direction the force is acting. So, that is why this current carrying wire shows the current in this direction like this. So means that current carrying wire bends towards me whenever if you are placing that into the plane there. For example, if the same thing if you are taking in the direction of which out of the plane current if you are taking. Out of the plane actually we represent with a dot like this. Now here again we are taking the current carrying wire which is upwards. As it is taken upwards here and again the charge we have to take is upwards, but this time the magnetic field is coming out of the plane here. So that is why here in this case now we will take the current carrying wire outside, means upwards like this we are taking the current, and the direction of the field strength is towards you, which is the current, the magnetic field strength is coming out of the plane like this we have to take. Then my thumb represents towards me to the right side here like this, okay, like this. Current carrying wire upwards and towards you the magnetic field is acting, and this side we are having the thumb is there. That thumb represents about the force acting. So that is why here this current carrying wire bends in this direction. So which is very clear that whenever if you are changing the magnetic field strength direction, the force acting is also changing. Now we seen in two different cases here how the magnetic force is acting, which is first case we took there as into the plane, of which here we are having that current carrying wire bends as it is of into the plane towards my left side it bends like this, it bends. And the second case we seen this current carrying wire, which is the current is taken again perpendicular, but this time I am taking out of the plane here. And in this case we got that the current carrying wire which is taken upwards again, as this is out of the plane, as the magnetic field strength is present, then it turns actually to my right side here like this. So it is very clear that if you are changing the direction of the magnetic field strength, there is a change in the direction of the force acting here. Now what we are doing is, this time we are changing the direction of the current here. So let us suppose this is the I is the current passing in both the cases. In both the cases I am taking the current is going upwards. Now we are taking the current carrying wire which is taken downwards we are taking, means first into the plane again we are taking, of which that into the plane we represent with the cross, okay, like this. And now we are taking the current carrying wire which is taken downwards here like this. We are taking downwards, and again as it is given that the current carrying wire here, it is actually that the magnetic field strength into the plane we are taking. And not only that, here we are taking the magnetic field strength is into the plane. So as the magnetic field strength is into the plane, means this middle finger we have to take into the plane here like this. And the direction of current actually it is towards downwards. So that is why here I am taking like this, as this is into the plane, and I am taking the direction of the current which is downwards like this. Okay, so into the plane it is going, and the thumb represents towards right side like this, which is downwards we are taking, and we are taking this middle finger into the plane we are taking like this downwards. Then the thumb represents which is pointing towards me, so that the force acting here is like this. So means we can get the force acting to the right side when you are taking just like here out of the plane case. Instead of changing the direction of the magnetic field strength, we can also change the direction of the current also. As you are taking vertically downwards here the current carrying wire, again the force is acting towards the right side we got. Okay. For suppose if you are taking the current carrying wire, taking again the downwards there, but now we are taking the magnetic field here which is out of the plane, and the direction of current is changed which is of downwards we are taking like this. Now this is the current carrying wire which is going downwards, but this time the field strength is different, just like this one, but the direction previous, that is of going upwards the current, now the current is going downwards. And again as the field strength is outside, this middle finger we have to take outside here, and this current carrying wire we have to take here downwards, that is, which is for example like this. As this forefinger always represents about the direction of the current here downwards like this, and this middle finger which is straight towards you, that is like this it is. Okay. Then my thumb represents to the other side here, to that side, like this we have. Okay. So that is why the force acting is just like this one here, of which we are having the magnetic field is coming, that force is acting that direction there. So means this current carrying wire slightly moves to that side like this. Okay. That is why if you observe here, this one and this one and this one and this one both appears to be same here. But if you observe here, into the plane, but the current acting upwards. This is out of the plane, the magnetic field strength, but the current is towards downwards. And this one into the plane here, but the current carrying is downwards. This is out of the plane, the current is acting upwards here. So means it is very clear that if you are changing the direction of the current, or if you are changing the magnetic field strength, always there is a change in the direction of force is acting. Now we are taking the example here, a numerical example having the current carrying wire into a plane here, so that we are taking the plane is into the plane, we are taking the strength like this, and we are taking a current carrying wire inside that. Let us suppose if the length of the wire is 10 centimeters we are taking. Okay. If the length of the wire of 10 centimeters if you are taking, okay, a current carrying wire having the length 10 centimeters carrying current, let us suppose you are taking 1.5 amperes, that is. Okay. For this 10 centimeters wire, as the current passing here is 1.5 amperes, let us suppose the magnetic field strength acting here, which is B, the magnetic field strength that we are taking, let us suppose that is of 10 power minus 3 Tesla we are taking. Okay, like this. Then what we have to find is calculate the force acting, and the direction of the current. Force acting with direction. Okay. Now the magnetic field strength formula we already know that, as force F is equal to, we know that is equal to B into I into L, that is. As F is equal to B into I into L, because here I am taking both are perpendicular to each other, that is why the force acting is maximum force is acting. And we know that B value is already given there, where B is equal to, it is given 10 power minus 3 Tesla, and not only that the current also given there, which is I is equal to 1.5 amperes, and whereas the length also given there, which is of L is equal to 10 centimeters, that is. As these are in SA system, even the length also we have to take that in terms of SA system, that is. Where that 10 centimeters, if we convert that 10 into 10 power minus 2 meters, which is 10 power minus 1 meters, that is. As F is equal to BIL, where B is equal to 10 power minus 3 and I is equal to 1.5 and length is 10 power minus 1, that is. Then total it becomes 1.5 into 10 power minus 4 newtons. Okay. So this is the force acting, which is of 1.5 into 10 power 4 minus newtons is acting on the current carrying wire. Now we got the magnitude of the force acting, but as force is a vector quantity, we have to give the direction also. As I said earlier, that force how to take that is, as the magnetic field strength is acting into the plane, which is like this, it is acting, okay, into the plane. So this middle finger we have to take into the plane, and as the current carrying wire, that current is going upwards, then we have to take upwards here, and the thumb represents you the direction of the force acting. So that is why if you apply the right hand rule here like this, the current carrying wire is upwards and the thumb is acting towards right side of mine, to the left side of mine, means in this direction. Now the current carrying wire bends, and the direction of the force is acting like this, of which how much is the force acting is 1.5 into 10 power minus 4 newtons is acting here like this.